Okay, 510 is, again, we're going to talk about some ratios. Okay. And this is in similar figures. Similar figures are based on ratios. That's how you see it. They are the same shape, but there is a ratio between the sides. Okay, so if I look at this, and I draw this, and then I draw this, these are similar figures. If they were drawn exactly correct, okay, means they have the same shape. My drawing is just not perfect. Okay, so they have the same shape, but they're different sizes. And so all of their lengths that you measure would be in the same ratio. So their side lengths are in a ratio. So one of the problems we looked at was that square, that it was 3 times longer. Okay, so this one, if I had this one as 1 and I said this was 3 times, okay, that one's 3, that would be a ratio of 1 to 3. So that means if this was 4, this would have to be 3 times bigger than 4, which would be 12. Okay, and if this one were 2, by the way, this does not work in a right triangle, so this triangle is not right. 2 times 3 would be 6. So the ratio of their side length is 1 to 3 or 3 to 1, depending on how you're describing it. Okay, the bigger to the littler, the littler to the bigger. Okay, so again, similar figures are when you have the same shape. It's kind of like what a scale model would be. Okay, a scale model is exactly the same shape. It's a replica, but it's just been scaled down. Okay, it's like a picture enlargement. If you look at a picture and you enlarge that picture, the shapes all stay the same, they just get bigger. And the ratios are 1.5 or 2 or whatever it is. And so that way you can see that they're the same, but they've made it bigger or enlarged it. Okay, so enlargements or reductions. Where's one place we use this all the time? Where can you think of scale models? What?
Trains, cars.
Sure, you can get scale models of all of them, right?
Oh.
We have actual, and they are by ratio. They'll call them 1 to 64th or 64th scale. That means it's 1/64th of the original size.
Fun fact.
Okay.
Oh, wait, no, that's getting off topic. I don't know what to say.
So trains, cars, planes, any of the models, okay, that we do for them. Okay. Now, a lot of people just like to do models of specific ones. There's not really a set thing. When do we use a model before we go to the bigger thing?
In architecture?
Yes, we draw models of things that are small, they're scale, so that people can get an idea. Yeah, okay. But they make a model, so in architecture, you do the model and then you make it larger when you actually construct. Okay, so that's in architecture. Okay, so they do that a lot. They'll do the concept building, the designers do a concept, They have the people that are gonna pay for it come in and look at the concept, so it's done to scale, so they can get a vision of it.
That's what my mom has to do all the time.
And then they get, that will then be constructed at a bigger scale, because we can't show somebody the scale thing without constructing the whole thing. I mean, you can't show him that whole thing. So we use that. Architecture, if you just even think about plans for a house, floor plans, I'll call it floor plans, okay? Those are then used to build the house. So in building a house, okay? So you go out and you construct. I actually drew the floor plans to the first house we built. And it was fun. I learned a lot. I learned how the scale drawings worked,
You
okay?
ever write like something on the wall, like on the floor, so when they do it, you'd be like, oh, I did that. I made them do that.
No.
Oh.
I was
Do you
trying to
do that?
design it so it could sell again if we wanted to sell it.
Okay.
But there are a lot of things you have to think about in building floor plans. Because you have to have structural walls that are supporting other walls, and you can't have too long a spans without putting beams in and stuff like that, okay? There's a definite way of how to construct your kitchen so you're economizing space, so that there's not as many steps used when you're, have to make a long trip over there and back. And so there's all sorts of different things. If you're looking at making it so it's long-term, or for somebody that's disabled, that's a whole different thing, because most of our houses are not made for disabled people, or for people that as they grow older can't navigate stairs, or they have to use a wheelchair or a walker. Until you have to use those, you don't realize how much is not constructed for you. Okay, they've constructed it a certain way for aesthetics, but it's not necessarily work for everybody. Okay, and so those are things.
It usually has to have a balance between usage and design.
Yes, yeah, it does. Okay, but anything that's public has to be accessible to people with disabilities. So they have to put those things in there. They have to think about that. How do we make it so it's accessible for people in wheelchairs? How do we make it accessible so that they can come on their own if it's a powered wheelchair? Okay, and what things do they put in there, which I think you see a lot. There's the disability openers for doors.
Has
They're
anyone
all
did this when they're
round.
younger, when they press that button, so
Yeah.
that opens the door? So
It
they,
just opens
Who
for me.
doesn't?
yeah, that's the real
I'm wondering, the question is, who doesn't do that? So that's one way. There's some other things that we do in similar figures. And if you'll notice in the book, if you turn to page 308, there's a picture there, and it's talking about the similar figures amongst babies, the infants versus the child. And here you see the ratio of the head to the length. It's usually 1/4 to 1/8, so it shows you that, which is kind of interesting. And then the ratio of the trunk to a leg. So the ratio of your trunk length, this length, the trunk, okay,
That's a
to your
trunk.
leg, yes, that's the trunk, is the same. So if you look at these, I can't tell exactly where their legs are, but on the infant it's 1-to-1, because if you notice the legs are 3 squares and the trunk is 3 squares. So from the neck down,
That's horrifying.
okay, to there.
Was that walked in the door on Big Baby?
But it's kind of horrifying to look at that big of a baby, isn't it?
You've grown up so much.
But
You just see a big
in an adult, your leg length is longer than your trunk. Okay, so your trunk is normally shorter than your leg length. So that changes. Okay, so those are just some proportions that we see. A lot of these, like I said, they're used in this aspect. Okay, they're used for modeling stuff. because we need to find out what we're gonna draw, or we need to picture what we're gonna make. So not just floor plans, they do models of all the different things that they make, like,
Our church has a big model, like, cause we're
are you at
rebuilding it.
Rushberry
Yeah.
Baptist? Okay,
Yeah,
so you're rebuilding it, and so there's a model there to show what it's gonna look like, and that's to scale. So all this, I don't know what they are, in floor plans, usually 1/4 inch equals 1
Oh,
foot.
maps. That's
Okay.
another.
Maps is another place. It's actually a scale drawing of what the area looks like, how the roads go. It can be a terrain map, so it shows you how the terrain is going over that area. Okay, so maps are another scale drawing thing that we do. Okay. One way we can use similar figures, and this is actually used to estimate some things. Okay, have you ever tried to figure out how do they measure the elevation of a mountain?
They have a drone, and then they fly it.
No,
all-
wait. We had elevations of mountains before then, but just think about, here's this mountain. I don't know what he looks like. He usually doesn't go up quite that fast when you make them a little bit more like our mountains here. They go up kind of like this and down, right?
Is that mountain red?
I have no idea what that is.
It's definitely not
But
the
the
same mountain.
elevation is actually from sea level. So sea level may be clear down here. This is sea level.
And that's why Mount Everest is the tallest, because the mountain range that it is sitting on is higher.
Yeah, so the height of the mountain isn't from where the ground is.
Really?
Yeah, it's from where the sea level is. That's elevation. When we're
So from
talking
the base to the
elevation,
top.
from the sea level up to there, okay? So how do they determine how far you're up if you have to measure it perfectly up? Yes?
Well, I was gonna say something else.
Oh, okay.
Do you think if, like, it were to be measured from where the ground is to the top, Everest would still be the tallest?
I don't know,
No,
I've never
no.
done, well, it depends, where do you say ground level?
Yes, that's true.
Do you mean the
Because-
base of the
Like the
mountain?
base.
The base of the
No,
mountain?
the
No,
it's
it's not.
the Mount Kilauea in Hawaii.
Yeah.
Yeah.
So is that one? I climbed that one.
Yeah, because that one is down low. So the problem with, when it's higher though, elevation, you get into other things like oxygen and pressures and stuff like that. So that makes a difference. But elevation is actually from sea level, wherever the sea level is, up to the top of it. Okay, so most people don't think about that. We just think that, oh, that's how much it sticks up right here. How much it sticks up, but that's not really what it is. Okay, so how do you think they measured that? Yes.
I mean, it's obvious. They got to the top and they just drilled straight down till they reached.
Yes, they did. They drilled right straight down through
What?
all that rock,
What?
and they
I've been lying.
measured it clear when they hit water. They measured it.
Wait, are you,
Wait, no.
Hey.
I think she's gaslighting.
wait. I think
Grayson, are we being truthful?
They probably
no, they start
looked
from the
at
sea
it.
level and then they go straight up.
And how do they do that?
They drill.
Here's a serious thing.
Okay,
Here's
yes.
a serious thing. Depending on how far away they are, they measure like this.
Yes, angles. Yes.
Yeah.
It's what we do to measure distances out to the sun and all those different things. So they have to actually get to sea level. And from sea level,
Oh,
they
measure
can
out.
use
Oh.
similar triangles. Okay? So what happens is you have to have a nice sunny day. But what you can do is if you're out on the sea, like the old all the old ships that they were navigating, okay, were on sea level. Okay? They were at sea level because they're on the sea. That's why it's called sea level. And water always goes to the same height. So our sea levels don't change.
Except for
Well,
slightly.
lakes are different because they're up higher and stuff. Okay?
That's not what I'm asking.
What are you saying?
Except for very slightly during the 200 years when it gets hotter and colder.
Well, okay.
We're talking about
Anyway.
water, not other water.
So, what happens, let's just kind of go out here, is if they're out here on the sea, away from the mountain, okay,
Can they see the mountain from the sea?
they'd have to do this.
Unless it was in the middle of the United States.
Well, that's harder.
Oh yeah, how
We'll
do
talk
they do
about that, we'll talk about that, then they can do measurements
Wait, that
from
line's
that.
lower than
Okay.
that line over there.
Oh,
It's a different sea level. I think
There. oh, shush. So if they're out here, what they do is they try to get they shoot a line up, okay?
A zip line?
Like
A laser.
a laser, well, no, it wasn't a laser, but you're basically looking out your periscope or your telescope or whatever you're looking at, and you can shoot a pretty straight line, okay? And then what you do is you find basically at the same angle, you find maybe the mast of your ship, and you know its height, okay? And then you know that these angles are the same, so we have similar triangles. If I were to go over here, now, this triangle is just much bigger than that triangle with your mast of your ship. You look for what is, so you're standing here where you have an actual length there, and then you can make similar triangles based on the ratio of these things that where you're at, okay? So that's one way of doing it. Now, we don't use it for mountains because it is a lot of complications, and I'll just say that the travelers that traveled around on the sea, they got to be able to do a lot of things. They mapped a lot of this world very accurately at a very long time ago, okay? They were very, very good navigators. They did a lot of it from distances to the stars and all that kind of stuff. They knew where their position was based on how the stars were positioned. And they made maps of our world that were very, very accurate without a lot of knowledge. They used basic, just simple tools to do it, okay? And that's basically where the word geometry came from. Geo is the same as earth. Metry is the same as measure. Measuring the earth, geometry. They used a lot of triangles. Triangles got to be, and that's one of the biggest things in
Isn't that also
geometry.
geology?
It is also geology. That's the study of the earth, because ology means study of. Okay?
So you're
Yeah.
saying with this way,
Measure of a
from the
state.
ocean, you can see Mount
I'm
Hood.
saying this is back with special techniques. You can't see all of them. But that's one way they could do it back before we had other things like imaging
So way back
and stuff
then,
like that.
if they wanted to measure that mountain, they'd be like, yeah, I'd say it's about a couple thousand feet.
They could.
A couple thousand feet for every mountain.
Yeah.
Couple
So-
thousand feet, couple thousand
No, a couple thousand.
feet.
They also did this, like I said, with different things for out in the skies. They could measure distances by the distance of something closer and the angles and that kind of stuff. So they came up very sophisticated ways of measuring things, but with very simple tools, okay? So one way, which is kind of fun, is you can do this if you have a sunny day. And this could be one of, so your project, you get a lot of choice on this time. You just have to use some sort of ratios on it, okay? Or probabilities, which are ratios, experiments, which turn out to be ratios, similar figures, body ratios. We're just using stuff with ratios, okay? But if you go out and let's say you want to know how tall the tree over there is. Okay, there's a tree over
You
there.
go to sea level.
No, we're not, we're looking at just the tree itself from the ground this time. We're not looking from sea level. Okay, so the tree, and it's too high to measure because you can't measure it, okay? But what you can do is if you can get the shadow from the tree on a sunny day, so the shadow of the tree, and let's say it comes out this far, there's where the shadow ends, okay? Then, if you know something, the height of something here, and it is being hit by the sun, so it has to be parallel. So you could put like a board up that you know how high it is, and get its shadow to end at the same spot. So you'd have to figure out where would that board be positioned. Okay. And so if you know this height, let's say this is a 4-foot board, and its shadow is 6 feet, okay? Then if you know the distance from here to here, okay, so let's say that your tree, you can measure how far your tree is from there, from wherever you're at the end of its shadow. Usually the shadows aren't miles long, okay? Let's say that, let's say it's 160 feet. Okay, you can measure it. Now, usually we don't go that far, but the sun is low down right now, so you don't get the steep shadows as much, you know, because of where it's at in the sky.
What if this tree, like, is on the side of a cliff? Knowing that
Then
it's a
I wouldn't try to measure it,
You
okay? No,
You wouldn't?
no.
Oh.
Unless
Would
I'm
you
on
do
the
like
other
that?
side. Well, it depends. Okay, here's the cliff, here's the tree. I'd be on this side.
But what if the shadow's going the other way?
I'd wait till the sun went the opposite direction.
Okay.
Why not just walk on the other side and start floating? Like humans can do
Yeah,
that.
well, okay. Anyway, because these are ratios, you could do 6 to 160 equals the 4 to x. You can figure out what the height of the tree is, okay? And the reason that works is because your angle is the same. The sun is shining at the same angle on both things, okay? Now, it's best if you can do it right around noon or so, because, or around 1 or 2 or 11, because that way is when your shadow is going to be the smallest and you don't have to do as much measuring. You're going to get smaller. It's not long. If you wait to do this till the evening, and around here it's harder to do because we don't always have the sun. Okay. So, but if that's true, you can find out the heights, okay, of that. That makes sense? Okay, so those are some things that you can do with this, okay? That's how we use measurements. We use geometry to measure things. We use similar triangles a lot of times to measure things, or similar figures to figure out what the heights of something is. And so there's a lot of that done in making stuff or in just finding heights of stuff, because people don't go out and say that tree right there, I'm going to measure it and take a measuring tape up and measure it. We do it more by approximation. We know that this distance and that distance, so we try to get them pretty easy so you can figure out the distances here and give a good estimate of it. Okay, so that's how they'll say that tree is so high. Okay. They don't actually go up and measure it, drop a measuring tape down from a a helicopter and see how tall is this tree. Because again, you want to measure the height straight up. We don't want to measure around it like that. That's not accurate. Okay. So, okay, it is time for a break.